Hello, so I'm going to pick up with where we left off in class with our code for producing Riemann sums, right? So let me minimize my picture here. So this is what we had in MATLAB, and in class we were using the function f of x equals x squared plus 4, whereas in the packet you're just starting with the function f of x equals x squared. Right? I did that to move the graph up a little bit, so our rectangles would have a little bit more height, so that they're easier to talk about. Okay. So in class, we talked about if we wanted to approximate the area from x equals 1 out to x equals 4 under the curve, we could add up the area of rectangles, because rectangles are the easiest geometric shape to use when finding areas. Okay, so if I ask you to add up the area under the curve using a left-hand Riemann sum with 6 subintervals, you would literally be finding the area of these 6 rectangles. So we talked about in class, if you go from 1 to 4, that's an interval size of 3. And if you divide that into 6 subintervals, they're each 1/2 of a unit wide. Okay, and we could literally take the height. Now notice all the heights are being determined by the left-hand side of the rectangle. It's the upper left corner that bumps into the curve. That's why this is a left sum. So you could take the first height times 0.5, the width, plus the second height times 0.5, plus the third height times 0.5, and so on, down to the last height. But notice the last rectangle, the last height is not all the way out at 4. That side never touches the curve. All right, the last height is at 3.5. So when doing a left sum, we won't quite reach the end of the interval. Okay, the 6th rectangle lines up one little step. The step size is the width is 0.5. So the left side is 0.5 before the end. Okay, so continuing with that. So we have these 6 rectangles, and you could add them up by hand. If we were trying to do 60 rectangles, it would be very difficult to do this by hand. So let's not do that. So with 6 of these, we could do a left sum by hand. But now we want to see, how does MATLAB do the sum? And in class we talked about, if I did want to do, let's just say instead of 60, let's say we did 24 of them. So we would be doubling that twice. Those rectangles are much closer to the area under the curve from x equals 1 out to x equals 4. So let me go back to 6 and see how that would influence our MATLAB code. Okay, so in the code, first of all, let's make sure we understand the parameters. The 0 to 4.5 is simply saying, let's graph a window that goes from 0 to 4.5. If I change this to 0 to 5, my window just becomes a little bit wider, and I still have the 6 rectangles just on a wider window. Given that that has a lot of, well, we'll just leave that. Okay, so that's just for you to scale your window so that you can clearly see all of the rectangles that are involved. All right. A tells me the x value where I begin finding area. B tells me the x value where I stop adding up the area. So you can see the red rectangles run from 1 to 4 because A is 1 and B is 4. The function, now remember it was a string, so that's why the apostrophes are around it, is x squared plus 4. We can change that to be any function that we want, which is why I put it in parameters. Okay, the things the user changes are what we want to have in parameters. Type 1 is telling us what type of sum we're doing. So you can do a left sum or you can do a right sum, and in fact I'll talk about some other sum types as the video goes on. Okay, 6 is the number of subintervals, which corresponds to the number of rectangles. Okay. Now be mindful, how many vertical lines are there? There are 1, 2, 3, 4, 5, 6, 7. In order to get 6 rectangles, we need to have vertical lines at 7 different points. So that's something important to keep in mind. 6 subintervals require 7 vertical lines. So just Keep that in mind. Obviously, if this were 8 subintervals, it would require 9 vertical lines. You always need one more vertical line than the number of subintervals in order to make these rectangles, right? NP equals 5001. It just needs to be a large number because that tells us how many points are on the blue curve, all right? We want to make that up with a large number of points so it looks like a smooth curve, all right? Now, there are 2 Lin spaces that we're going to create. You'll notice the comment, okay? The first Lin space is going to be used in generating points for the curve. That's what line 19 says. Whereas the second Lin space is going to generate the points we need for the rectangles, okay? So to get a smooth curve, we need at least hundreds of points. Thousands is probably overkill, but that's what I did. But in order to generate the points for the rectangle, we're going to require 7. If we want 6 rectangles, we're going to need to evaluate this at 7 different x values to get our 7 vertical lines, okay? So the first Lin space, notice it uses NP, the 5001 points, okay? So that's going to give us a lot of x values. We put those into x so that when we evaluate the string of the function, the string had x as the variable. So we're going to assign all of the thousands of x1 values into x, and then we're going to get corresponding y values. So those will give me the x and y values for the blue line. Then we want the corners of the rectangles. So we're going to start at A, because the first rectangle is at 1, and we're going to end at B, which is 4 in this case. And we want 7 points. N plus 1 is 7. So that will be 1, 1.52, 2.53, 3.5, and 4. That's 7 x values. We plug those into x so that we can evaluate the function that's given, and we'll get 7 corresponding y values, all right? Now, how wide dx is how wide the interval is, all right? We talked about this in class. In this case, we have an interval that goes from 1 to 4, so that's 3 units wide. We're dividing it into 6 subintervals, so that will end up giving us a dx value of 0.5, and you can see our rectangles are spaced by 0.5s, okay? The next little bit of code is for the graphing. For plotting, we need a maximum and minimum x and y for the graph. This bit of code you don't need to worry about too much, but it just says if the minimum y is actually a positive number, our graph should go all the way down to y equals 0. That avoids having graphs that start at y values bigger than 0, okay? And likewise, if the maximum y is negative, all right, that would mean all of the y values are negative. We would still want the graph to have the x-axis in it, which is 0. Okay, so that little bit of code is going to guarantee that we include the x-axis when we go to set the axis command in the plot right here. Okay, so we want to make sure that y equals 0 is part of the graph regardless of whether it is always positive. If the values are all positive or all negative, we still want y equals 0, also known as the x-axis, to appear in our axis command. Okay, this plot statement's pretty easy. This line right here takes, remember, x1, y1 were the thousands of points. It creates a blue line for the function. All right, this line of code is going to create an x-axis in black. All right, so this line of code creates the x-axis. We go from the left side of the screen to the right side of the screen with y values of 0 at both sides of the screen to get that axis built in there, okay? The next line of code is going to, let's see, what is that going to do? Oh, that is going to put in the y-axis, okay? So if we had an x-min that was negative, we would want to include a y-axis. So this line of code goes from, it holds us at an x value of 0, but it goes from the bottom of the screen to the top of the screen and puts in another black line, which would be the y-axis if the graph doesn't start at x equals 0. Okay, and then this is the axis command. So what did this plot statement do? It gave us the graph of the function, the blue line on placed on top of an x and y axis, right? And then you turn your grids on so that you get a little grid behind there. Okay. Now it's important. The hard part of this graph is actually drawing these rectangles. All right. So we need to, before we do a second plot statement in order to have a left sum, we need to hold the graph still. So what will the command that do? It will mean that as I draw more plot statements, the old plot won't be erased. Without that hold, if you put a second plot statement in, it erases the first plot statement before it does the second plot statement. Also, before going into any kind of loop, all right, we're setting the total area equal to 0. Before we add the rectangles, we want to start at 0. So we're basically clearing the memory of any pre-existing area calculation and resetting it to 0. Okay. Now our cases are based on the sum type we're doing. So for right now, we're talking about the left sum. You're going to change this left sum into a right sum in just a few moments. But for now, this is how the left sum works. Okay. The plotting part, let's worry about the plot. Okay. Notice we're going from 1 to n in the loop. So we're going to go through this loop n times, that's 6 times. Each time we want to plot one rectangle, okay? So, in fact, let me do a little pause. I'm going to add a pause command instead of draw now. I will pause for 1 second. I'm going to change that back to draw now in a little bit, but if I run the code right now, see, each time through the loop, we add one of those rectangles. So it kind of slows it down enough so you can see how there's 1 second between loops. And each loop produces one rectangle. I'm going to change that back to draw now. And it just sort of builds in an automatic pause statement where with only 6 of those, it draws it very quickly. But they were being plotted one at a time. So this takes us through the loop 6 times. The first time through the loop, IT equals 1. And the last time through the loop, IT will equal 6. So what this plot statement is doing, let me change my window so you can see it fully, is we first need a vector. Remember, we're doing the first rectangle. Okay, it has 4 corners. So you'll notice that we have 1, 2, 3, 4 x values that are going to be connected. Okay, so the first x, here's the first corner. We're going to connect that to the second corner, to the third corner, and the fourth corner is down here. So we want to draw these 3 red lines for the first rectangle. Okay, so where is, if we're doing a left, I'm sorry, to draw that rectangle, the first corner will be the first, the x value of it is at the first x point right here. Okay, so this is the x of IT. Remember, IT is 1. So this is x1. Okay. The second corner, we're going to do all the x values first in the first vector, is still at the x1 value, the first one. Then you'll notice we switch over to IT plus 1. Well, when IT is 1, IT plus 1 would be 2. So the third corner is at the second x value. Okay, the second x2 value. So that would be x2, 2. And then the last corner is also at the second x value. So notice that also has an IT plus 1. Okay, so when IT is 1, IT plus 1 will be 2. So we take the first x value and the first x value and the second x value and the second x value to get corner 1, corner 2, that's still at the first x value, corner 3 is at the second x value, and corner 4 is also at the second x value. Now, what are the y values of those corners? That's what this vector is giving us. It gives us the 4 y values. Well, the first corner is at y equals 0. The second corner is at the height the first height, okay, y2 it. That would be, since it is 1, it would be the first height. Now, whereas the third corner, it's also at the height of the graph at the corner over here, okay, which is still the first height value. Okay, so even though we're over here, we're using the first height value, not the second height value. That's what makes this a left sum. We're using the first height value again, all right? And then we drop down to y equals 0 for this bottom corner down here. So MATLAB will pair the first x value with the first y value and create a coordinate. And then it'll connect that to the second x value and second y value, which is a coordinate, and the third and the third and the fourth and the fourth. So MATLAB will compare those vectors to give us the 4 corners of the graph, and it will connect those with red lines. Okay, so that makes the first rectangle. When n switches to 2, it'll take all of the it values will be 2, and the it plus 1s will be 3. So we'll take the second x value for the first vertical line, and it'll take the third x value to get these corners over here, and the y values will all be at the second corner right here. Okay, so we'll hold that y value as we go across to produce those rectangles. Now, in this loop, we're also getting a cumulative area. So we're going to take the area of the first rectangle, and we're going to add it onto the area that was already there. So for the first rectangle, there was no area already, and we're going to add it onto 0. But then when we get to the second rectangle, we're going to be taking the height of the second rectangle based on the left sum times its width, and we'll add that onto the first rectangle. And the third will be added onto the cumulative first and second, fourth onto the first, second, and third, and so on. So by the time we get to the last rectangle, we're adding that onto all of the previous areas to get a total area. Okay? Now, we're creating a string that we're going to add into the title of the graph. Okay? Now, case 2 will be the right sum, which we'll talk about in a moment of how you can do that. Okay. Now, down here, so we'll pop back to case 2 in a moment. It hasn't been created yet. In order to create the title up here that says left sum of x squared plus 4 with 6 subintervals on 1 to 4 equals 29.375, we concatenate a bunch of strings. Okay, so title string tells us what kind of sum it is. Okay, T string, remember, is left sum, but if we go to case 2, that will be right sum. And then the function, okay, is a string, so it will put whatever function has been typed into the string, then we literally add the word with, and then we add in the number of subintervals, but we have to convert that to a string because n is a number, so we num to string it, and then we just put in another phrase, subintervals of all of that. So you can see that shows up in the title. And then we have to put the a value into the bracket, which is in this case 1, but we have to num to string it because we have to make it into a string. And we do the same thing for the b value. We want to put a little comma in between, so that's what this part of the code does. We want to put a bracket on the end. Okay, so we're just putting together a lot of strings. Okay, and then finally, we're going to put in the area as a string to tell us what the area is. So this is a pretty complicated concatenation of various things in order to get the title that shows up on the graph. But you actually won't need to do anything to that when you're making other cases. And then the last line just sets the font size. So what you need to be able to do in the packet is do left. We know how to do left sums. Now we want to be able to convert all of this to a right sum. And it's pretty easy to do it. The right sum is almost the same as the left sum. So all I'm going to do is take all of this here, since I'm going to make a right sum, I don't need to start over. I can copy this. And let me, before I make any changes, I am going to save my code as a different version. So I'm going to save this as RS student I'll call this 2021. Okay, just so that this is our class modification right here. So I'm just making it into another version so that I don't lose what I had before. Okay, and right here, I'm going to take all of the stuff that had been in the left sum and I'm going to put it right here under right sum. Now, obviously, if I make no changes, case 2 will end up doing exactly the same thing that case 1 did. Okay, so case 2, it will pick case 2 if the type is set to 2 instead of 1. So in the parameters, if I select 2, now it should do a right sum. Now, how do I make this into a right sum? Okay, it's still a left sum because I haven't changed anything, right? If I want to make this into a right sum, okay, I want to still plot exactly the same rectangle sides, okay, but I don't want the tops to be based on the left, okay? So this is the first thing that has to change. For instance, I don't want the first height to be based on the first x value. I want the first height to be based on the second x value. And then I'm going to want the second height not to be based on the second x value. I want it to be based on the third x value. So I need to shift these up by 1. So I just have to make them +1 and +1. All right. That means down here, what height do I want to use when calculating the area of the rectangle? It's not going to be, I'm going to have to make that +1 as well. All right. And those little simple changes, changing these y's to be the next y value instead of the one that we're on, it +1 means the next one, will turn all of this into a right sum. So let me run it again. And remember, I'm on type 2. And you can see that just gave me a right sum for the same area. And you can see this is clearly over top of the graph. Okay, so when I did a type 1, that was left sum, because the graph is increasing in value, the left sides are under the graph. But if I change that into a type 2, the right side, we're using the right sides now. The right side of every rectangle is above the graph. So we changed our rectangles over, okay? And let me go back real quickly. Look at the area. We can visually see that the left sum should be too low. So notice that's a little below 30. If I switch it to a right sum, the area under the rectangles is more than the area under the curve, and that's about 37. So the area is somewhere between 29 and 37. If I want to get a better sense of the area, I could use more subintervals. So let's, instead of 6, let's go to 24. And if I do a left sum, that's going to be close. It says the area is 32, but I know the area is actually going to be more than 32. If I turn around and do a right sum with 24 subintervals, I get something that's, about 34. But I know the area has to be less than 34. So the actual area under the curve must be between 32 and 34. I'm closing in on what the actual area under the curve is. Okay, so that's where you're going with this. Okay, now you could see that to switch, all I had to do to change from a left sum to a right sum is, instead of using the y value at the left side, I'm going to switch to the y values at the right side, and all that required was that I make it it +1. Okay, so my rectangle heights are based on the right-hand side, and my rectangle widths. And I'm sorry, and the area calculation is based on the heights of the right-hand side. Now, one final thing, let me go back to making this a 6. I want to point out which rectangle height is no longer used. Notice we no longer use the height at x equals 1. The first height that is used when I do a right sum is at 1.5. And notice now we do use the height at x equals 4. That will correspond to so the final height of the last rectangle is all the way at the right-hand side of our interval. But the first height was not at the left side of the interval, right? So another interesting fact is the first rectangle for the right sum, let me switch this to a left sum, is exactly the same height as the second rectangle of the left sum, right? And the last rectangle of the left sum, notice its height was found at x equals 3.5, corresponds to the second to last rectangle of the right sum. So the right sum has an extra, its last rectangle was not included in the left sum. And the first rectangle of the right sum, of the left sum was not included in the right-hand sum. So the only difference between the two is the first and last rectangle. So that will come up in working through the packet. Okay, I'm going to start another video then to talk about other types of sums. This is enough information to be able to do the packet, but I'm going to use one more video that talks about moving on to other kinds of sums.